All right, so let's go ahead and get started with some questions from you guys. Any questions that you'd like me to go through? I have the practice exam on me, and solutions are also posted. Any questions that you'd like me to go over? All right, so let's just go ahead and I'll just start in. I've got some problems from starting from chapter 2 through chapter 7, and I'm just going to work through some of these problems. So chapter 2, this is number 15 in the book. It says, here are the life expectancies at birth in 119 countries, 2014 as collected by the World Health Organization. So we're supposed to describe the shape. So that this would be, it would be left skewed. Well, let's just describe the entire distribution here. So the distribution of life expectancies in 190 countries, 2014, is left skewed. I'd say bimodal with peaks at so it looks like these are every 2 years. So 70, 72, at 74 and 80. Years. A center about, and it would be better to get like a mean. Sometimes you'd have like a summary stats given to you, and then you could just give the mean, or in this case, it'd actually be even better to give the median because it's left skewed. Center at about, I'm just going to say 80. No. More like, I'd say more like 70. And as far as the standard deviation goes, well, let's just say most values and most life expectancies are between 68 and 80. Years. All right. How many modes? It's 2 modes. Question?
Describe the peaks. Say peaks at 74 and 8. You also say there are peaks at you know, for the
the countries?
Yeah.
Okay. Yeah. So the question is if we should use the X variable to say where the peaks are, or if we should use the Y. This is actually a frequency here. So we would want to use the X variable to locate where these peaks are, just because The frequency, it may be confusing because there may be several different spots where you have 20 countries. And it's also not the variable that we're interested in. We're interested in the life expectancy here. Yeah. Yeah, so the question was, should we use coordinates, like x coordinate, y coordinate? And it wouldn't make sense to use that in this case because it's not a scatter plot. But you could say how tall those bars are, and just as a little extra information. So you could add that with peaks at 74, with about 30 countries. And then at 80 years with about 20 countries. About 20 countries. All right, so it's okay to give some extra information there. Just realize the most important information is the life expectancy. Question? No. So the question is if you'll lose points if you don't describe the shape like this. And for a problem like this, you would not lose points because it's actually only asking for from about above this line is the shape. So it's left skewed and bimodal. But generally, a question will ask for just a description of the variable, and then you'd want to give the shape, the center, the spread, if there's any unusual features, and there's none here. So. Okay. Any other questions? All right, so I'm not doing chapter 1 because I'm not gonna, so on the test, I'm not gonna ask direct questions about what kind of variable it is, but you need to know that in order to know if you're going to use like a scatter plot or a segmented bar chart or a, so maybe it's just spur of the moment here. This scatter plot. This has two quantitative variables. Segmented bar chart. So this has an X and a Y. This one goes up to 100%. And this one looks kind of like that, remember? So where you have and this there's a little legend there, and then you'll have labels, like A, B, C, and this is two categorical variables. There. And then, let's see, you could have a side-by-side box plot. Just talking about some of the different graphs we've had. So this has some kind of a variable, like This is like A, B, C, and then here we've got like some kind of a quantitative variable there. So this is one quantitative and one categorical variable right there. And then there's other ones, of course, like a histogram. So histogram, that would be just one quantitative variable. And then, of course, there's, maybe I could fit this in here, a bar graph. And I kind of running out of space. And that's a bar graph. As one categorical variable. And then there's other ones too, like a dot plot, that's quantitative variable. A box plot, that's quantitative variable. A stem and leaf plot, that's quantitative variable. Any questions with these? Oh, right. So, yeah, so the question is, where are the categorical variables for the segmented bar chart? So remember we had a contingency table, kind of like this, where let's say we had A, B, and C, and then we have numbers like these. And these are frequency counts, so which one, how many fall in each of these intersections. Oh, this one's actually, it's got 3. Yeah. And so we've got like whatever that one is, those categories. So here, one variable is for each of the bars. That's a categorical variable. And then the other variable is for the percents of each of those bars. And then how you would find these is you do conditional distributions. Additional distributions here. That's how you'd find each of these bars. And that's where the numbers come from, is from the frequencies within each of those. Does any questions with that? I could go a little further down the rabbit trail or the bunny hole. Either one, the rabbit trail or the bunny hole, if you want me to work with these numbers. Is that good for you? All right, it makes sense. All right. So we're in chapter 3, and this is yeah, we'll actually get some chance to work with these, because this is a, looks like we've got 2 variables here. So we've got, I guess this variable would be like demographics or like things about movies. And then this variable would be the ethnicity. Yeah, I would call this demographics over here. And then this would be an ethnicity variable. So we want to compare the conditional distribution of ethnicity for all 3 groups: the entire population, moviegoers, and ticket holders. So the conditional distribution of ethnicity for all 3 groups. So this sounds to me like that is the condition, is that you're in one group, or you're in another group, or you're in another group. So the conditions are going like that, like that, and like that. Okay. Well, that's not very neat. Well, I don't know if that made it easy to read or not. You get the idea here. We're working with the rows. All right, so we would want conditional distribution for, let's do for, well, maybe we'll do it this way. So for population, for moviegoers, and for tickets. So those are the 3 rows there. And then here we would have, I'm just going to do C for Caucasian. And then I'll have 204.6. And then we're in the rows. So this is 310. Hispanic, African American, other. 49.6 over 310. These are in millions. And 18.6 over. Am I doing this right? Oh, did I mean to? So the total, you can think of it as a statistic. So it actually comes from these numbers over here, and all it is just the sum of all those numbers in the row. So it's not really like you're adding any information when you're circling the total. It's just a nice thing to know because you use it in the denominators for all of these. So it's not wrong to circle the total, and it's also not wrong to not circle the total. It's, in my mind, it's connected though, because that's the total of the row. So and we use it. Okay. The trickiest part with this one, of course, is making sure you're going in the right spot, so you have the condition right. So this is over the ethnicity variable, and then the condition was each of these groups one at a time. All right, so I think I'm doing it right. So I'm just going to write all these fractions out, and then I'll find the percentages. Oh, yeah, that is true. Oh, right. Yeah. So the word is for. So that is like a condition. You're only using those. You're only in those groups. Do you agree with me, or would you argue elsewhere? Because it is pretty confusing. Like, are you leaning the other way towards the columns? Oh yeah. So the reason why I did rows was because of this word for. And that makes me think that it's these groups that are the condition. So compare the conditional distribution of, and if you said the groups for all the ethnicities. Yeah, so it really depends on just where this word is, or if it's switched with that. So in this case. So the main thing is that you have the condition there, and that's what tells you if you're in a row or a column or where you're at. So if you can figure that out, what the condition is. Okay, so I'm just going to crank out the rest of these. Can you see that? Oh, yeah, you can see that. Hispanic is 26.8. And then we've got 16.9. And then we've got 8.5. And then for tickets, we have 728. And then over 1,300, age is 338. 143. And then 91. So if you do all of these guys, 204.6 divided by 310. And then we do the moviegoers. We get 0.63, 0.19, 0.12, 0.06, and the last column here. Yeah, so this one's a little, like, it's a lot of work here. But let's just finish it off. We're almost done. 91. And then I want to draw the segmented bar chart since we have all this information here. Because we want to write a brief description of the association between ethnicity and moviegoers. These ones? Yeah. You could write them as percentages as well. So I think when they say moviegoers here, they mean the variable over here. So like about the demographics of the moviegoers. So here we've got three things here. We've got the population. We've got the moviegoers. And we've got the tickets. And then we've got 1.0, 0.6, 0.8, 0.4, 0.2. And population, let's just start, well, these are bars. Let's start right there. And then let's do the Caucasians. They go up to 0.66, right about there. The moviegoers, they go up to 0.63. And the tickets, they go up to 0.56. So this one is the Caucasians. And then we've got Hispanics, 0.16, So that would be go up to 0.92. And then for the next one, it would go up to oh, I added wrong, 0.82. Right there. This one, I'm adding 0.63 plus 0.19 is 0.82 again. And then here, this is it's 0.82 again. And then we've got African Americans. You add 0.12 to that, that'd be 0.94, which is just way up here. Here, 0.94, and somewhere around there. All right, so as far as any trends that we see, you can see that the blue is going down and down, down as you go to the right, and then the purple here is getting a little bit bigger as you go to the right. Yeah, so that would mean that the Hispanics they buy more tickets. Each of the Hispanics, they buy more tickets than for each of the Caucasians, they buy less tickets. Right there. And as far as the population, comparing it with the population, it's about the same with the moviegoers. So yeah, I don't think it's very useful to compare there. Any question? Mm-hmm.
So why do we have tickets and population there? Because from my interpretation of the question, we just be looking at the moviegoers row.
Right. Yeah. So what I'm trying to do is usually when you say there's a association, it'd be between two different variables. Does that make sense? So as something is happening in one variable, maybe something else is happening to another variable. And that's why I decided to split them up like this. And I agree with you that this doesn't, it's not, these aren't like super related. They're just like different groups. So this, I don't even know if you could consider this one variable. Actually, now that I think about it, like it doesn't make sense that this would be one variable, because the cases would be the p. Well, here it would be. So with this column, the cases would be the tickets, and then whether the ticket was, which ethnicity had the ticket. And then here, the cases are people and people. All right, question? Yeah. 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 Yeah, I agree with you. Between ethnicity and moviegoers. Yeah, I would just say that the majority, yeah, just what you said. The majority of moviegoers are Caucasian, and then there's some Hispanics, and then there's. But it's useful to look at the population as well, because you see that a larger, the Caucasians are less likely to go to movies than Hispanics are with the ratios. So that's interesting to me, I think. Is that interesting to you as well? Right, so if we look at the tickets, so here, so moviegoers just mean that if you just go to the movies, maybe some people don't go to the movies at all. But then here, the Hispanics got a little bit larger here. So they're hitting above their weight as far as their fraction of the population. So right here, this is the fraction of the population that are Hispanics. But then a little bit more of those. So the ratio increases here, but then as you go from population moviegoers, it decreases for Caucasians. So another way of saying that would be that a larger fraction of Hispanics go to movies than Caucasians. Oh, tickets. Yeah, but then sometimes you could get like 3 tickets, 4 tickets. Maybe you go to 5 movies. So you'll notice this number is really large. So there's 1,300,000,000 tickets sold. And then as far as the moviegoers, there's 141 million. So that means that each moviegoer gets about 10 tickets in the year of 2010 is what this is. Yeah. All right. Any other questions with this? I kind of want to just move on to another problem. I think we spent enough time on this. Marginal, you just work with the totals. Yeah, I think. Unless anybody wants me to do the marginal real quick, I could do that. You're all cool. All right. Chapter 4, yeah. All right, so this one we've got a side-by-side box plot going on here. And this is cost of living in 2016. 576 cities. Prices are in US dollars, so you could have $1, $2, up to $6 for water, eggs, and cappuccino. All right, so in general, which commodity is the most expensive? And you would look at the medians to figure out what tends to be the most expensive. So here the medians are the little bar that's in the middle of this box. So water has a median of about 1.08 or so. Eggs has a median of about 2.28 or 5. 2.25, somewhere around there. Cappuccino, it's higher, so it's about a little less than 3, like 2.8 maybe. Right there. Yeah. So cappuccino tends to be the most expensive. All right, and then the next one. Is a carton of eggs ever more expensive than a cappuccino? Yes. Because here we've got eggs has the highest. So whatever country this was in, no matter what point it was over here with the cappuccino, that was lower than the eggs price for this country. All right. Yes. The max of eggs price is higher than the max of cappuccinos. Yeah, so you look at the outliers as well. So those are legitimate points. They just have stories attached with them. They're out there, so to speak. Yeah, you wouldn't know for sure though. Yeah, so to answer this question, you want to be confident that in 100% of the cases. So that's a good question. So you could have here, maybe that's country 1, but then maybe this is also country 1, and the cappuccino is higher. And then here, country 2, maybe it's still higher over here. And I guess in the case of this guy, the eggs, the lowest, the min, you could still have the cappuccino be higher up there. But for this country right there, country 4, we know that the eggs price would be higher somewhere over here. Say it's over there. So you could still argue that without the outliers, just in the case of country 4 on the low end of the cappuccinos. Because they have such cheap cappuccino that the eggs it has to be more expensive. Mm-hmm. So you have to be careful with that. Like if this was a little higher, then you wouldn't be able to confidently say that in all cases that holds. All right. Which commodity has the largest range? So this one, you just look at the, you use the outliers. That's the key part here. So here we've got water has a range of about 3.8. Eggs has a range of about 5. Cappuccino has a range of about 5 as well. But I would say the eggs is more like 5.2. Eggs is a little bigger than the cappuccino. So I would say eggs about 5.2 range. Yeah. No, these are dollars. Oh, I guess they go over here. $2 range. All right. Any questions with this sheet? And then we can go to chapter 5. Chapter 5, I have 3 parts to this one because this is the one with z-scores and normal distributions. Oh, a question in the back. Oh, one more time, please. Oh, yeah, sure. We could just skip straight to 7. Yeah, where's it from? You don't need to know how to compute it by hand, but you need to, so the question was if you need to compute the least squares formula. And so you don't need to be able to compute that by hand, but you do need to know what B0 and B1 is, what's the y-intercept of the formula, and what's the slope. And you need to be able to write that in the context of the problem. But no, you don't need to, you're not going to be typing in a big list of numbers and finding the least squares line yourself. Okay. Oh, yeah. So, yeah, as far as being able to find R, yeah, the formula is on the exam. If you needed to find R using B0 and B1, yeah, you totally could. So, yeah. I haven't looked at the practice exam yet. Yep, with the formula. Yep. Same form. It's exactly the same. So I just copy pasted it over. So the practice test has the same formulas as the exam one. All right. No one's gonna ask me how long it is. 6 pages, just like the practice test. Yeah, so it's 3 pages front and back. Yeah. So, any other questions? All right, just so maybe try to do the practice test in an hour and a half. So that would be a good. Hopefully, it doesn't take you 3 hours. So, okay. Chapter 5, Part 1. So here we've got this one's a z-scores one, and we've got French and mathematics. So in French, she scored 82, and in math, 86. And then we had a mean of 72 and a standard deviation of 8 for the French. And then for the math, she had a mean of 68, a standard deviation of 12, and an observed of 86. All right. So then on which exam did she do better? Let's do French. And we just need to find the z-scores is what this is. So recall z equals observed minus mean over standard deviation. All right, so let's call this ZF for French. Observed was 82, mean was 72, standard deviation was 8. Well, I can do this in my head. 10 over 8 equals 5 over 4 equals 1.25. No units on z-scores. All right. And then for the math, let's just do the same thing. Let's call it ZM for math. We've got observed 86, mean 68. And of course, you got to know that she's going to do better on the math than the French. I mean, this is a math book, right? Let's hope so, at least. 86 minus 68 divided by 12 is equal to 1.5. So she did do better on the math. Good job, incoming freshman. She did better on the math test compared to her peers. All right, any questions on that? So if you're comparing how unusual it is, like what's more unusual, that kind of question, z-scores. That's the easiest way to do it. And the z-scores formula is on in that formula box on the last page of the test. All right, let's do one with the 68, 95, 99.7 rule. All right, so here we've got, we're doing some IQ tests. Question? Rescaling, so like, oh yeah, like multiplying all the data values by 3 or stuff like that. Yeah, you will need to know about that. So Yeah, just know what, so the question was, do we need to know about rescaling? And yes, you should know what happens to the mean, median, standard deviation when you multiply by some kind of number like 3 or by 0.5. Or let's say you add or subtract the same number from all of the data points. You need to know what happens. The mean, the median, the standard deviation, the range, all of that. You should have some kind of understanding. And the easy thing with this is you can always just work out a quick example. So give yourself a data set. The number is 1, 2, 3. And then it's easy to find the mean of that. It's 2. And then you could add numbers to each of those. So add 1 to each of them. So it'd be 2, 3, 4 would be your new data set. And you find your new mean, and it would just be 3, which is 1 more than the previous one. So you can just do a quick little test with if you forget what happens if you multiply or what happens if you add and rescale that data set. Yeah. Yeah, examples are great. So draw the model for these IQ scores, clearly label. So here we've got we start with the mean, which was 100. And then we want to, oh, yeah, it's actually working pretty good. You can find these guys. And pictures are great for showing your work because then the grader can see what your process was and what, like if you had the picture correct, and could give you some partial credit if you happen to lose your way. 70, 55. So these are IQ scores. All right. Showing what the 68, 95, 99.7 rule predicts. So we got this guy. We've got this guy. And we've got this guy or lady. 68%, 95%, 99.7%. All right. So in what interval would you expect the central 95% to be? So that one would be between 70 and 130. About what percent of people should have IQ scores above 115? So you'd want to shade in this little region. Right there. And we could use the rule here. So here we've got 34% right there, just on the right half. And we've got 50% on the entire left half of the normal distribution. So of course, we would take 100% is everything, subtract off 34, subtract off 50. So 100% minus 50% minus, well, 68 divided by 2%, which is 16%. All right. Any questions with that? About what percent of people should have IQ scores between 70 and 85? Okay. So here we've got 95 divided by 2 is right here. And then 68 divided by 2 is this white space here. So the way I would do it is I would take 95 divided by 2 right here. And then I would subtract off the white space, which would be 34%. So 95 divided by 2% minus 68 divided by 2% is equal to 47.5% minus 34% is equal to 13.5%. All right. Any questions with that? There's other ways to do it too. Maybe it could. Let's try it another way, huh? Let's say that you. So what's past this guy? Let's see. What's a good way to do it? Okay, I've got another idea. So if you take like this, one, two. So this right there is 95% minus within one standard deviation minus 68% equals I went down too far. There we go. Equals this, which was 30, was that 27%? Right? And then you would want to divide that by 2 so that you get just one. So then divide by 2. Oh, I've got white out. Bam. Divide by 2 to get just the left side. Which would then be 13.5%. That's one way to think about it. It's another way. All right. Can anybody think of another way? Normalcdf. Don't use Normalcdf for this one. Oh, yeah. That is another way. But you would want to use the rule in this case because a Normalcdf would be a great way to check your work just to make sure that you actually got it. And it should be plus or minus like, I don't know, 1%, let's say. It should be pretty close. But with the problem like this, since it's specifically asked for, we should use the rule. All right. Well, maybe I'll just draw it over here on this side. I'll just do it the first way again. I'll do it in blue. So the first way I did it was I had 1, 2, like that, minus that is equal to just the part we were interested in. Right there. And the numbers work out as well. This was like 47.5% minus 34% is 13.5%. Any questions with that? Are you getting the same thing? All right, let's do the last one. About what percent of people should have IQ scores above 130? So with that, let's go back to up here. It's this little spot right there. And you would subtract off this from 50% is how I would do it. So subtract off 95 over 2 from 50%, the entire right half. So 50 minus 95 over 2 equals 2.5%. Right there. All right. All right, cool. Any questions on that? Do you want me to go over that a little slower? The last one there? All right. It's funny, I look out and it seems like it hasn't quite sunk in, but no one wants to say anything. That's what it seems like. I could do another example with this rule. I'll just do another one. So let's say here's a nice fresh normal curve ready to be shaded in. 1, 2, 3, 1, 2, 3. So let's say this is 50. Oh, I can make it hard. Here, maybe this will confuse you. 10, 20, 30, 40, 0, negative 10, negative 20. So it's okay if there's negative sometimes. It's just a model. So don't worry about it. And let's call this grams. Just leave it at that. Okay, so what proportion of the normal curve is between negative 10, so this was the mu, the center, negative 10 and 40 grams. All right, so it's not quite the same. So here we go, 2 standard deviations over here. But here we've got to go 1, 2, 3 to get that guy right there. All right. And we want to use the 68, 95, 99.7 rule. All right. So let's see, probably the easiest way the easiest way I can think of is to split this sucker in half and find that and then that. That's the easiest way I can think of. So the left half would be 95 divided by 2, and then the right half would be 99.7 divided by 2, and just add them together. So A equals 95 divided by 2%. B equals 99.7 divided by 2%. Area is A plus B. Oh, made a mistake. Or 47.5 plus whatever that is. 99.7 divided by 2 is 49.85. And so add those together, and you get 97.35%. All right. All right, so that's my last one for that one. Let's do part 3 now. Chapter 5. So here, this one, we're going to use some normal CDF and some inverse norm. So we're going to bust out the calculator, finally. All right, so we've got, suppose the heights of kindergarten children can be described by a normal model with a mean of 38.2 inches and standard deviation 1 inches. What fraction of kindergarten kids should the company expect to be less than 3 foot tall? Did I say that right? Less than 3 feet tall? So that'd be 36 inches. So let's just draw. You should always draw a nice little normal model here. And then find what those are. Plus 1.8 plus 1.8. So that is 40, 41.8, 43.6. These are inches. And then the other one, minus 1.8, minus 1.8, and again, 34.6, 32.8. All right, so 36 inches is right about here, and less than means you shade to the left. And then we would want to do normal CDF. So second distribution, normal CDF. We're shading to the left, so negative 10 to the 99th is the lower bound. And then it goes up to 36. The mean is 38.2. Standard deviation is 1.8. And so it would be, for A, it would be 0.111. All right. Yeah, right there. That. So about 11%. 11.1%. B, in what height interval should the company expect to find the middle 80% of kindergartners? So there, let's just, well, maybe we'll do B over here, huh? So we want 80% to be here, and then 10% there, and 10% over here. All right? The middle 80%. So it's exactly in the middle, and it's got 10% on each side in the tails. And then we need to find X, and we need to find Y right there. So we would use inverse norm. Inverse norm because we're given the percentage, and we're given this area instead of being given the specific height. And we want to find the height though. So let's just find X. So inverse norm. And here we've got 10% to the left. So that's what we stick in here as a decimal proportion, 0.10. The mean is the same, it's 38.2. The standard deviation is 1.8. So you type that in there. 0.1, 38.2, 1.8, 35.9 inches. All right, happy? I hope you're happy. 0.1 is 10%. And that's the area to the left of that bar, this bar, X. Yeah. 10%. All right. And then here, the area to the left is 10% plus 80%. That's how you'd find Y. Norm, which ends up being 0.90. And let's just put in 0.9. And you get 40.5 inches. All right. Any questions with that? So the answer to the question for B would be between 35.9 inches and 40.5 inches. All right. That's where you'd expect the center, the middle 80% of the kindergarten to be. All right. So to review with that, with part B, is we took 100% minus 80% is 20%. And then since we have the middle 80%, we have 10 or 20% divided by 2 is 10% on each side. And then we used inverse norm to find where those values X and Y were. And of course, we drew the picture so that we knew what we were talking about. So, yeah, always draw a picture for these normal model ones, so you can just know what's going on. At least how tall are the biggest 10% of kindergartners? So that one, we can just use our previous picture here. And we see that the biggest 10% are where Y is, which was 40.5 inches. At least 40.5 inches tall. All right. Any questions with that one? So in review, if you're given the value, like on the normal model, then you use Normalcdf. If you're given the area as like usually it's a percent or something, you would use inverse norm to find the value, where it lands on the normal model. All right. So let's get on to chapter 6. So I've got 2 pages left. So I got chapter 6, and then I've got one for chapter 7 as well, and we can call it good for tonight, unless you have more questions. All right, chapter 6. So here we've got some burgers. We've got the fat in grams, and then we've got calories. So here the fat in grams is the X, and that is explanatory variable. It would tend to explain why the calories are so high, is because of how much fat is in the, because fat has a lot of calories, I mean, as far as per gram, more so than protein and protein, carbs, yeah. Protein and carbs are less. Analyze the association between fat content and calories using correlation and scatterplots. So I'll just say that I would say that this is, it does look to be linear. And it's positive. I would call this a moderately strong relationship with an R value of 0.961. So the association between calories, or between fat in grams and calories, capital C, calories, is positive, linear, and moderately strong. Yeah, that's all you need for that. So it has the direction, the form, and the strength. And then of course we have context. So this is, oh, I should have said that this was in burgers, in hamburgers. Yeah, there's some more context. It's not just any food, this is hamburgers. All right. Any questions? And of course there's more to chapter 6 than that, but I'm just gonna, oh, question. Form. So it's either linear or nonlinear are the things that you have to pay attention to. So if it's linear, it makes sense to talk about correlation. If it's nonlinear, then it does not make sense to talk about correlation. And you can tell that just by looking at the pattern. It's kind of, you know, going up and to the right in a somewhat linear fashion. The R value? Yeah, so the question is, how do we know if it's moderately strong as opposed to very strong or weak or moderately weak? And it is the R value. You can look at this. I prefer to look at just the dots themselves, the scatter plot itself, and see how tightly packed the dots are. So something like this, not that tight. But then if it was more like that, that would be like strong. And this would be like weak. And if it's all the way to the corners as well, then that's just like there's like no correlation there. Because then it's just all over the place. So, all right. Oh, negative R values? Yes. Yes. Right. Yeah. So if with an R value close to 0, it'd be like no relationship or weak. And then with the R value that's negative, that just means that it's, instead of going this way, it's going down like that. And of course, it can also be strong. So I'm just repeating this for any listeners. Any of you online. Okay. Next chapter. Here we go, chapter 7. All right, so here we're back with, oh, well, actually this is birth rates, so not hamburgers anymore. Birth rates. Big difference. Okay, so we're supposed to make a scatter plot and describe the general trend in birth rates. So a question like this, you'd be given a scatter plot on the test. You don't have to make a scatter plot because that would involve a time consuming. Well, it doesn't take that long, but it could, it could take a while. But yeah, you'll be given this. But you should be able to describe the general trend in birth rates. So for A, Yeah. So it's linear, but then it's also, as the years progress, the birth rate goes down, is how I would say. And that just means it's negative. So the general trend for the birth rates can you see that? Yeah, all right. Is that as the years pass, the birth rate goes down. All right. Find the equation of the regression line. So that one is just, it'll be given to you. So that's right here. But you should be able to write that as in the context of the equation. You will see that on the test. So here, in the context of the equation, or the problem, that's what I meant. In the context of the problem, so you only have to write it like this if it specifies, and it will specify. So you would write birth rate. So this is the response variable, and that's the predicted birth rate. So we got a hat on there. Is equal to 25.6 minus 0.114. And then here we have the years since 1900. That's just the X. That's the explanatory variable. Yeah, good question. So there's a couple ways to know. A big hint is what you're trying to predict. So here, maybe we're trying to predict the birth rate. It wouldn't make sense to say that we're trying to predict what year it is. We just know that. Yeah, so what you're trying to predict will be the response variable. And that goes here, and it has the hat on it. Yeah, the y-axis. So the response variable always goes on the y-axis. And then the explanatory variable, usually like 95% of the time, if you have years or time or days or something like that, it'll end up being on the x-axis, because usually you're not trying to predict what year it is or what time it is. It just doesn't happen like that, unless you're like a time traveler. And you really have no idea what year it is. Yes. Yeah, so sometimes they may just give you like the slope and the intercept, the y-intercept, and you've got to piece it together. Yeah, so y-intercept is 25.6. The slope is 0.114. And of course, there's units along with that. So let's just work down the line here. So C, is it appropriate? Yes, because the points are somewhat linear, or have a somewhat linear pattern. All right, and D was we need to interpret the slope of the line. So that we would want to say for every year since 1900, the predicted okay. So we would not want to say since 1900, since we want the slope is the same all throughout the line, you know, all over the line. So let's instead say for every additional year. We want to make sure you get the units in there though. For every additional year, the predicted birth rate in the United States goes down, or you could use the word like decreases. Would probably be better. Oh, goes down by and then here we have the number 0.114 births per 1,000 population, per 1,000 people. So I'm just reaching back up here to see what exactly the rate is. So it's the rate of births per 1,000 people. So here on the y-axis, if we're kind of confused with what's going on, you say, okay, so this rate means 18 births per 1,000 people. And that's I would assume it's a yearly birth, like how many births in a year, I would assume, is what's going on here. But that's the end of that sentence. So, any questions with that? Oh, yeah. So what it is, it's how steep. So the question was, does the... Oh, no, I'm just trying to rephrase your question so that people... No, let me just say it so people can get it, the people on YouTube. Okay, so the question is if the number 0.114 falls somewhere on the graph. And the answer would be that it tells you how steep the line is. So negative slopes go down and to the right. Positive slopes go up and to the right. And then if it was like a larger number, say negative 0.5, it would be more steeply negative. So every year the birth rate would be going down more sharply. So it's not like an actual point, it's how the line is oriented. All right, E, the table gives rates only at intervals. Estimate what the rate was in 1978. So this one, we have to use the equation we have. So y hat equals 25.6 minus 0.114 times, and then this is since 1900. So we would put in a 78 in there. And then type that in. Let the calculator do the heavy lifting. All right, 16.708. Let's just say 16 point. Well, we've been keeping 3 decimals up there, so let's keep 3 decimals down here. 16 point. Oh no, don't give out. And we've got units here, so it's birth rate. Yeah, birth rate. In 1978, just seeing, repeat that. All right, so in 1978, the birth rate was actually 15.0. How close did your model come? So with that one, you would want to this is called a residual. So let's recall residual equals observed minus the predicted. Yeah, I ran out of room. Okay, well, okay, and the letters E equals y minus y hat. That's in symbols. So here we've got the observed was 15.0, and the predicted was 16.708. So this was a over prediction, and that was turns out to be 1.708 births per 1,000 people. All right, and that's what the question was asking for. Oh yeah, this is negative. Yeah, but since it says in F how close, that's like an idea of distance. So it doesn't say what direction. So it'd be fine if you didn't give a positive or negative sign for what direction. But a lot of times the question will be asking you, is it under prediction or an over prediction, and so that sign does become relevant. Any questions to cap off the night? Yeah, we can. Let's see, correlation coefficients. Like as far as like how they're how to work with them, or like what let's look at some examples of different possible correlation coefficients. So here we've got X, Y. So this is correlation coefficients. Let's say we had kind of the same thing here, but then a number like a dot like that. And then let's say we had something like that. So this one, well, let me just write some correlation coefficients. Like that. And then you may be asked to be able to match these together. So here you see that this one's negative. And then it seems moderately strong. And then here is another negative one. This should be the same, except for it's weaker because of this rogue, the outlier here. So here we've got two negative R values. So the stronger one goes here, and the weaker one goes there. But then here, this one is a little more chaotic. It's got less of a relationship. It's like, I would say this is a no relationship, and a value that's close to 0 is like that. Did you want to go a little bit over R squared maybe as well? It may be on the exam. Let's do it. R squared. So let's say you had R squared equals 0.95. R value equals, oh, there we go, equals what? I don't know. And as always, you would like, ideally, you could actually see the scatter plot so you could see what's going on here. So here, let's say it's something like, that right there. And so to find the R value, you would literally take the square root of this. So R equals the square root of R squared equals the square root of 0.95. And then it's important to notice that it should be a negative R value because the points are going down. So that's one way that you could try to trick you. So square root of 0.95 equals 0.97. Well, let's just call it 0.97. But since the relationship is negative, R value is equal to negative 0.97. All right. You can see the negative sign. Yeah, negative 0.97. All right. Any questions with that? Let's see. I could do another thing. Yeah, question? Yeah, let's just. Equal spread condition. I can tell you that that's not going to be on the test. And I, just off the top of my head, I'm drawing a blank, honestly. Yeah, question? Oh, that would make sense. Yes. I would go with that, but it's not going to be on the exam. Any other questions? All right, let's just call it a night. Thanks for coming. I hope this helps you and that you all do great.